chicken to cook it.
Oh, yeah.
It's absurd.
Like how much energy would need to be exerted into...
Can you stir a
Serious
cup of coffee
scientific
to heat it up?
answers to absurd hypothetical questions.
Exactly.
Well, the problem is if I'm stirring it to heat it up, but at the same time incorporating cool air. But yeah, so I might need to pick up a copy of that book. All right, but I need to get us started on our lesson. Maybe we can talk more about that after class, or like at the end of class. Did you need? Well, once I get them done. Do what?
Fraction.
Back there behind the parabolical Earth, if I have any.
All right, thank you.
Or hyperbolical, whatever that one. Right cabinet door. Yeah. Right side of that. If the 8th graders ever brought them back, because they've been coming to borrow cards. So the thing about this air cannon that he makes, or this water balloon cannon, is he is setting a specific amount of pressure every time. So he's operating on like a certain threshold, and if everything goes right, and we've counteracted the force of friction, at least consistently every time they like oil up the barrel before they put the balloons in, we can get some pretty consistent results. So this is where we talk about projectile motion. Now, aside from if you've watched Family Guy and seen the terrible scenes where there's projectile something happening there, who can explain why we use the word projectile? Why don't we just say motion? And I don't expect you to know. I would just, you guys impress me
Because
all the
it's a
time.
moving object
It's a
not
projectile,
on the ground.
not a motion.
It's a projectile, not just a regular old object.
Okay, but still, why?
Is it an object
It's
in
more
motion?
specific.
It is an object in motion, but so when an object is in motion, I guess better question, what is impacting it? Keep going. Friction,
Friction,
Air.
gravity, air resistance.
gravity. Gravity. When an object is in motion on Earth, it's being impacted by gravity. So, why we use the word projectile motion is motion that is being impacted by gravity. So, when we talk about like miles per hour, that's a rate of speed, right? Gravity is not really impacting you driving 150 miles in 3 hours. Yeah, there's a little bit of friction happening, but your speed is not being changed by gravity. It might be changed by friction, but it's not really being changed by gravity. If I throw something in the air, that's being impacted by gravity directly. And gravity can change my motion, right? So if my motion starts going up, gravity has the power to completely turn it around and bring it down. Projectile motion. So Sasha uses this idea to create her own water balloon cannon, and she has the results as shown on your resource paper. Now, our task today is to be able to determine her average rate of change. What is average rate of change? Well, I'm glad you asked. It is the slope between any 2 points will give you the average rate of change between those 2 points. So if we talk about speed in this problem, is that going to stay the same? No. Right? The object is going up, 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 stop, down, 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 down. Right? Like, it's not consistent the whole way through. So, first thing we're being asked is calculate the average rate of change between half a second and 1 second. Then, we've got a couple more extension problems, but until we do average rate for that first one, I don't think we really need to think about those. So, work together. Make sure you agree on your answers before we move ahead. So, start with B, and let's process through there then. I'm not going to answer questions about C. Okay, I don't really want to answer any questions about this at all until you guys have worked on it for a few minutes. Excuse me.
Mr. Hudson, can you get me a book, please?
You need a book. Why do you need a book?
I can't see the
You don't need to
1
see that
second
yet, though.
and
Oh.
5 seconds.
Well, you've got that data on your graph paper. or on your
no,
graph.
I can't spell 0.2.
Oh, so wait, you mean sometimes you need the graph and the table?
Besides, isn't this?
Oh, sorry, that's Jen's. We're on Sasha first, right? Sorry, that's what I get for having you guys get those in the beginning. We're using the table. So we can graph Sasha's parabola on this paper if we want to. But right now, what we're using is the table. Sorry, my apologies. I forgot to specify that.
It says
The
to
next-
graph the data. Should we do that? still?
Yeah, you can do it on this paper. Yeah. That's why I went ahead and gave it to you.
Oh,
So after, when, based off the table, when does it look like her balloon's the highest? For for Sasha.
Well, it looks around 2.5,
Yeah, around 2.5, right?
but maybe a little bit less.
Yeah, how can we tell that it's not quite 2.5?
Because
because
the 88.4 and 88.
Yeah, the 88 and then the 84. Okay. So, go ahead and try to graph that. Oh, wait, maximum height. We have maximum height given to us. So 2.5 was almost at our max height, right? Just barely not there. Wait, that still doesn't seem... I still don't know if that's perfectly symmetrical. We're graphing that data, and we have the maximum point. I just don't know that it's perfectly symmetrical.
Well, we know when it lands at 4.8 seconds. Because D tells us. How am I supposed to?
That doesn't make sense to me.
Maybe that's not really the maximum height.
No, remember we said trust the math.
We must.
Think about that. Why would this not be perfectly symmetrical in its parabolic shape?
Oh, wait,
air
is
friction.
Because the 90 points.
Did we figure out our average velocity between half a second and 1 second?
Maybe
Yes.
gravity, because while it's going up, it's like counteracting the gravity, but once it's going back down, it's going along with the gravity.
So, slow that down, say it again, and bring in the graph. Like, talk about the graph.
Um,
Slowing down as it goes up and speeding up as it goes down.
On this graph, that was a very concise way to say that, yes. Gravity is slowing it down as it goes up and speeding it up as it comes down. So, if we look at our rate of change between half a second and 1 second, a 1/2 second span. Well, his half a second was 34.5. So we have 0.5, 34.5. His 1 second, her, was 60.3. How do I figure out that velocity? Well, how do we talk about velocity? Yeah, in this scenario, feet per second would make sense, right? Distance over time. So feet per seconds.
So we've got
25.8? Or is it 26.8? I think it's 25.8.
Oh, yeah, and then you have to multiply it by 2.
Yeah, because the data that we have, so the velocity here, not of Jen, remember we're doing Sasha, but we're doing it on this graph, is 51.6. Well, we're going to call that V1. And we're going to label that feet per second. Also, if you see FPS, normally that also means feet per second. But I like just using the slash label. Let's look at another half second span on the way down, similar to the two of those.
Would that be 4 and 4.5?
Yeah, or 3.5 and 4, whichever one we want.
I did 4 and 4.5.
I'm doing both.
36.2.
What do we get if we do 3.5 to 4?
It's not at 34.5, it's at 34.2.
What? Wait, what?
Or at half second, it's at 34.2.
Oh.
So it's actually going at 52.2 feet per second.
Oh, this is a 2 you're saying.
Yes,
And this is
52.2.
We've got 33.
what? Oh, yeah. Because this will be bigger. Yeah. So sorry, 52.2.
Yep.
See, simple mistake makes a big trickle.
23 is 20.
About 44 in that span. I mean, check my math. I make mistakes. But I think it's about 44. I mean, 43.8, right? Wouldn't it be?
Yeah.
Then down here, ooh, these numbers work nicer. Between 38 and 18, or sorry, 48 and 18, it's 30 over a half. So this is 60. So we've already explained why this is happening. But now in the span of half of a second, our velocity on the way down speeds up by about 16 feet per second. On the way down, our velocity speeds up approximately 16 feet per second.
That doesn't make sense.
On the way down, our velocity is speeding up by approximately 16 feet per second.
Hold on a moment.
on the way down. Why? What is 16 feet per
That's the
second?
gravity.
That's the gravity.
But that's not Earth. They're not on Earth.
Are you sure?
9.8 meters per second per second. That's Earth gravity.
Oh yeah.
16 is not 9.
Yeah.
16 feet per second is not equal to 9.8.
So,
They're getting smushed.
Jacob, sorry,
No, they're
Chris.
on the moon.
we will look at why that happens, but here in this situation, that's what makes sense for us, right? The gravity impact is speeding us up by about 16 feet per second. We can also compare that on the upswing, or up travel, whatever you want to call it. It should be slowing us down by approximately 16 feet per second, right? So, agreed. On Earth, we've been told that gravity is 9.8 meters per second, but that's under ideal situations, right? Like perfect, no friction,
And
no,
it
like,
varies from city to city.
yeah, how far away you are from the center of the Earth. So all of this to say, ooh, wow,
Maybe, but even then, that wouldn't
Shooting
be
it off
something
Mount
different.
Everest.
that was not.
Like
Why
nine-
Probably
did
be a
you
lot
do
more
that?
wind though.
Maybe the balloon
90.
froze when it was coming down, so it got heavier.
9.8.
I don't think it left our atmosphere.
No, but
That's
the
what
Himalayas is really cold. So
All right,
it froze.
sorry, we actually spent too long on that. On your own, calculate the average rate of change at 1.75, like the velocity at 1.75 seconds. 1.75.
What? I got 85.
Can you show the rest of the table?
Yeah, sorry, I'm moving stuff around.
Per second?
Talk with each other.
So 34.2 to 60 is 56, and then 1 to 1.5 is 36,
Hey, Chris, at what time are we looking for our speed?
and then I'm going to say the next thing. I was going through it because I didn't remember which one was on.
Because I think you were working with these 2 points.
1.5 and 2 is 20 feet per second.
Now, why do you say that, Chris?
Because that's what we were doing the same thing. We're doing the average, yeah, it's the average rate of change between them, right?
Are you sure that's the velocity at 1.75 though?
It's not. You can probably do better, but it's. Let's get without doing calculations. Stuff.
Now wait, what were we saying we were calculating using those 2 different points?
Wait, hold on. Average rate of change.
Average rate of change, right? Which
So that's not like the exact.
average is saying there's high values and low values, and we want middle value. So if you use 1.5 and 2, and we average these values, well, do we think the average, and we know it's not median, right? We know it's not dead middle, but would average be pretty close to our trajectory at 1.75? Because what can we say about the trajectory at 1.5 compared to the 20 feet per second we just found?
The trajectory would be about in the middle of 78.4 and 88.4.
Right, but at 1.5,
Yeah.
the speed of the balloon at 1.5.
It would be lower. It would be slower. It would be, or no, it would be faster, sorry.
This would be greater than 20 feet per second, right? Because it's on the up. This would actually be less than 20 feet per second because the 20 feet per second is in between them. So since we're averaging, we're going to have a bigger value and a smaller value. This will be somewhere really close to 20. Not exactly, but really close. How could we get a better approximation for speed for 1.75? Because we know 20 is not perfect.
Find the equation for this half of the graph and then go through it.
Find the equation. What do we don't have the equation yet?
And
What could we ask for? What do we normally do if we're in Desmos when we want to know something more about like a part of the graph or something?
Click on this side of that one.
We can click on it, but even if I click on it, do what? Put a line at like use a line at the point that I want. Can I like even on Google Maps? What do you do on Google Maps if you want to like
Zoom in.
zoom in? Right now we're using a gap of half a second. Could we tighten that gap up if we had more data?
Yeah.
Yeah.
And we have the in between.
So I was debating having you solve what's the trajectory between 1 and 2.5, because still that's going to average to 1.75, right? So if we look at this trajectory, that's still a gap of 1.5, right? So it'll average into the 1.75. That's 30, right, approximately? 30.2.
Yeah.
So, but then that's for 1.5, so I got to divide it by like, that's 1.5 seconds, and so that's, well, that's still 20, right? So if it's 30 for 1.5, because still we're zoomed out, right? If we zoom in closer to the gap, we'll get a more accurate reading. So
you have 1.75 then.
you wouldn't want 1.75 actually. You want like 1.7 and 1.8
I mean, yeah.
because you need motion, right? You need it moving.
No, but I mean, like, we have 1.75.
Yeah, but then
No, but that doesn't tell you your rate of change. That tells you where you're at, not your rate of change. This is Maggie's balloon, by the way. It was Sasha's footage, but it's Maggie's balloon. We know it's not Jen's balloon. Okay, that's all we care about. So
here's Jen.
let's move on to Jen. So Sasha graphed Jen's launch, and you have it here on your paper. So instead of having a data table, we follow with a camera, and we graph the launch. What we do know is it landed approximately after 4.9 seconds, which it's pretty accurate for being approximate. Max height was 96 feet. You might throw that label on your graph so you know what it is accurately. Time is still on our x-axis, feet is on our y-axis. So now without a data table, you decide what you're doing to determine your average rate of change at those timestamps. So essentially, what is D going to be asking for? Essentially.
Like, just starting.
Starting velocity, essentially, right? Because if it's right at the beginning of the time, it's essentially our starting velocity. I'm going to give you a few minutes to work on this because I know you got to find some data points and stuff like that.
Asking for it right here. I think we do need rulers. Rulers would be helpful.
Get one if you want.
I'll smack you over my boy. Ruler snag. You want the short one? You get the short one. Okay, fine. I'll take the short one. Honestly, it's probably better because look at this. Perfection. I have the short one back. Oh, darn.
It has been given, cannot be taken.
I mean, yeah.
That's not the point, Chris. Let's see.
There could be those. Don't bend them. They'll end you.
About 12.5 feet at point 2.
So here's what's problematic. Is when we used to determine rate of change, like at 2 seconds, we could just easily go to our location for 2 seconds, do rise and run, and we're good. It doesn't work here anymore, right? Because we're not linear. So we have to make.
Like nice kind of.
You what?
A quadratic graph. It's not even nice kind.
It's not even nice, kind of.
It's
So,
not even a nice kind.
make it nice-ish. And if I'm looking for 2 seconds, like right in there, you want me right or no? Apparently not. I could either go back to exact second marks, or I can try to go to exact feet marks. So if we want to average, we could do like 1.5 and 3, or sorry, what do we, the first one's 2?
Feet marks might be easier. Feet marks might be better.
Compare it. Try it. If you did it one way, try it the other way. I don't know why my smart ink decided to stop working, but I'm going to try to get it back.
Reality is often disappointing. Smartly does not. Smartly mean it's not always word.
It's all showing up over here.
8.2 seconds. So, 62.5 feet per second is about 1.1. That's an average between 12.5.
So if our graph was linear, we could just say like, I don't know, 93, 94. I should have snapped the picture so we could see more of this. Sorry, I did. Almost like a perfect 95.
That's 92.5.
Or yeah, sorry, you're right. So if we decide to use perfect feet marks, make our life easy, that is 90 feet, but at what time?
Ain't no.
Well, so this is 1. We have 1.5.
That's about 1.865.
Yeah, see, that's the issue, right? 1.7?
We can measure.
Something like that.
Well, we could put it at something so that each thing is like a centimeter, and then we've got it like we can measure really easily.
Could.
So we can
As
scale
long
this
as
all
it's
down.
scale.
Perfection.
Except for
Where's that look to be? 2 point. Well, if we want to make our life easy, we could call it 2.2.
I think your smart board might.
It's off orient. Yeah, I need to reorient it. I'm just waiting to
really bad.
have a minute. Make it 2.2. How long's the time?
Half a second.
Half a second, right?
I'm scared.
And the vertical change there was
5 feet.
5 feet.
So that's 10 feet per
So
second.
that's approximately 10 feet per second. Notice our speed up here is like halved compared to our speed down there. Now, I know we're comparing two different.
feet per second. So.
Yeah, I know we're comparing two different balloons, right? We just did Maggie's and we found about 20 feet per second. But, like, this goes to justify what gravity's doing, right? It slows us down. So then, what if we go to try to answer 2.5 seconds?
it's like practically zero.
Now, I agree, but let's use our brain power.
We can use the. Which points did we already get for this?
You know what the vertex is?
Yeah, so we've got 2.2
2.45
and
96 is the
like 2.15.
Wait, how do you know that, Thomas?
because 4.9 divided by 2 is 2.45.
No, wait. Didn't we say these aren't necessarily perfectly symmetric, though? Because gravity?
Gravity's dumb.
That gosh darn gravity.
And it has to heckin' work too.
Stupid Isaac Newton. He's really
The inventor of gravity.
he really screwed up the world for us. We could have been flying around, but no, he just had to go and make gravity.
Yeah, but then how would we have all this stuff?
We wouldn't.
Right
We'd
now.
just be floating. It would be like this, except everyone would have like a rope or like an anchor to the earth, and they
No, they wouldn't.
clip it to whenever.
No, they wouldn't.
All right.
Yeah, but how
If
about
we zoom in,
There's rotation.
now you can't, right? I get it, but if we zoom in 2.5 right here, do we look like we're still going up or going down?
down?
Look like we're going down now.
So,
Thomas, you might be right that 2.45 could be our center because it looks like we're coming down already now. What if I used the point where it crosses the 95 feet and the point where it crosses the 95 feet?
that's what I was looking at. And it's 2.2 and 2. It's like 5. No,
We won't get
it's
any
like
answer.
2.65.
Chris, slow yourself down. If we use two heights that are identical,
0.
0, right? If we balance by using our nice heights, we're of course going to get 0 because we have 95 and 95.
So yeah.
I mean, you
So
can
we-
find the vertex.
So we can't. Well, maybe. But, so we got to use a couple other points. You should get approximately 1 here. Or about, like, maybe -1.
2.4.
Depending on what points you use, you're going to get slightly different answers. So then, let's tackle, what about at 4 seconds? 4 seconds.
You know what? Thomas is right. It's 2.45. It's the middle. The average.
And gravity should keep it even.
4 seconds is right there where the cursor is.
If you just reflected it, then it'd be the exact same. Because say it's slowing down at the speed of gravity, just like that is slowing down the speed of gravity.
Yeah, but
And that's
watch
speeding
it.
up. That
Okay, so
well, that's slowing down the speed of gravity. And that's
I don't know.
so it should be the same.
Maybe, but
What if there
see,
was
it's not different. Like the gravity when it goes up, it starts with a certain amount. It goes up to however much, and then gravity stops it. And then gravity accelerates at a different amount going down. Yeah. So it goes up. It's deep.
Everyone.
Why do you think they're both wrong? Join in the conversation. Don't just talk smack.
I don't think he has anything. I don't think he thinks we're both wrong. I don't know though, because it is decelerating by the force of gravity plus wind speed, or wind friction.
Yeah, I don't think that they're actually accounting for wind friction in this.
Hey,
But
they
they
should
might
be.
be. Yeah. But the friction would be the same going up as it was going down.
Maybe. But yeah. So I don't know. Maybe you can't reflect it. Doesn't seem like it is. In our last graph.
What goes up must come down. Spinning wheels.
So the question that we're arguing right now, right, is a parabola caused by gravity gonna be symmetric?
Maybe we should do this in real life.
We have to have some
Let's
sweet
make a
computer
blue
systems
cannon.
and cameras.
I mean, we could just go in and like animate it fine.
Can you imagine if you could make one of those like foot by foot panel boards and like as tall as like Kilbourne Stadium, and then launch stuff like, you know what I mean? Because you would need like foot by foot grid to be able to track. Like you would need some sort of grid, huh?
I mean, just figuring it out, just to like see it, just to like judge that.
We can make our own.
So, one thing, I bet there are at least a couple of you in this room that have never heard of Blood, Sweat, and
Mr.
Tears.
Hudson, can you go back to the other thing? I want to see something.
So anytime we do the parabola with gravity lesson, I always, like, that song is in my head, so I just wanted to play it for you. But that song's called Spinning Wheel, where it talks about what goes up must come down. So if we're saying that gravity on the way up is slowing us down at 16 feet per second, and gravity on the way down is slowing us, or speeding us up at 16 feet per second, that does create an interesting argument. Thomas?
So if we basically created a perfect situation where gravity is 10 feet per second, and then you start, say, throwing it at 100 feet per second, then it would slow down at 10, and after 10 seconds, then it would stop, and then it'd speed up 10, and then once it got down to the bottom, then it would be at...
So 10 seconds, it reaches the top, right?
And then at 20
Well, it
seconds...
depends what your initial velocity is. But
We're starting at 100 feet.
Yeah, we're starting at 100
100
feet.
feet per second, right?
Yep, and then the gravity is 10 feet per second.
Okay.
But it's not just 10 feet per second. It's 10 feet per second.
Per second squared, but yeah.
Per second squared. So it's accelerating by 10 feet per second every
Well,
second. Yeah.
it's decelerating.
Yeah.
When it's going up.
So when it's going up, it's going down by 10 each time. But when it's going down by 10, then 20, then 30, then 40.
It is gaining that much in its rate. Now, this does bring in the idea of terminal velocity, though. So, what I don't know why I keep calling Chris Jacob. What Chris is talking about can be iterated here. Sorry, I don't know why I keep freezing my screen either.
Just the same as it does.
So, in this situation, what did we say gravity seems to be? 16. Right, so what Chris is saying is when I start coming down, what goes up? That's horrible. If I go for a second, there? About how many feet was that?
It looks around 16.
Or no, that's...
It looks around 16.
I was thinking about it.
Now if I go another second,
That's half the yeah. You gotta go all the way down there to the 30 feet.
how far does that look to be? Approximately 32.
Yeah, but then do it on the other side of the same.
Right, but so what we're saying, Thomas, is you only had one error in what you were saying. The rate is constantly changing by the amount of the gravity.
Yeah.
So it's so what you said was true, except for the fact that Chris's part needs layered on.
Different.
Yeah. So we are speeding up at 10 every second. So your max there would not be at 10 seconds. Your max there would be quicker. Because you'd slow down by 10 in the first second, then slow down by 20 in the next second.
Well, 20
Slow down by, if you're using your gravity that you would describe.
Yeah.
Right? And then slow down by 30, and then we keep doubling until we reach terminal velocity. So if you throw an object
Fast as it can possibly go.
out of a plane, it is not going to continue speeding up all the way until it hits the Earth. It will create like a crater.
Yeah.
Fun fact.
Why?
Because air friction.
Air friction. Right?
Fun fact,
So stop bending your ruler. Put it down on the table. You obviously can't handle holding it. I get it. Bendy things are fun to bend. But I told you specifically, do not bend these. They're Mr. Parabolas. So we then have formulas that we can deal with terminal velocity, but we will take this trajectory until we reach terminal velocity. So 9.8 meters. You guys are arguing like 9.8 meters, right? And you're like, well, that's not correct. 9.8 meters.
16 feet may be
Wait. Okay, that makes sense. I just want to find it. Alright, coolio.
Gravity in feet is 32 feet per second, approximately, right? We're not dead accurate.
So this is half gravity.
3.28.
I don't know, we're going to keep talking about why this situation is what it is.
Gravity, that sounds good.
Half of gravity, that could be
I
fun.
can jump double the height.
Except that would be bad.
So if we allow this to be parabolic, and we can fit this on our graph because his doesn't go as high, put Owl's balloon launch on your graph. Put Owl's balloon launch on your, we have a minute, put Owl's balloon launch on your graph real quick.
So, 81 at 4.5.
Well, be careful. It's not 81 at 4.5. It landed at 4.5, max height of 81.
Wait, where's Al's launch?
We're putting it on the graph. It's in problem 75. We're putting it on the graph.
So if you launch something up high enough and it reached terminal velocity, then it wouldn't be symmetrical.
So here's, well, when you launch it, it's never going to reach terminal velocity when launching.
No, like it launch. Yeah, that's what I'm saying.
Yeah, then coming down, it won't reach terminal velocity coming down because it doesn't have enough time.
That's true.
It'll need more time than what you gate because gravity, right? Gravity's determining terminal velocity. This is a super deep conversation. We got to stop this because we're out of time. Tomorrow, where we're going to pick up is right here. Now hold up, because if you want to try this challenge and especially to work on your homework, if we know the vertex and we know our zeros, we know everything necessary to determine the function. Yeah? So this is where we're picking up tomorrow. If we know the max, or the vertex, and we know the zeros, we have everything needed to determine our function.
As long as
Mr. Hudson, can I lend you this book for?
Yeah, I'll take it home this evening.
you do that.
If you don't mind me taking it home for a night, because then I might just get on Amazon and order a copy.
I'll
If this is
get
a
one
book worth having in my classroom, I'll buy it just to put on my
I'm
shelf.
gonna get one too.
So good.
It's amazing.
You what?
I'm gonna get one of those.
You're gonna get one? Well, let me know if you want me to order it for you. Like, if that would save you time or anything.
Sure.
Great.
I mean,
Wait,
you need to bring me money, but
Yeah,
I'm an
I know.
Amazon Prime member, so if I order it on.
My
Here,
dad
well, I'll
was
look it up
too.
on Prime real quick and see what it
I
costs.
suggest-
this one is sort of related
I
to
suggest the mole of moles as your
The mole of moles.
Yes.
That one's my favorite.
Yes.